All right, so let's look at some of these practice problems. These were chosen because I felt like they were similar enough that they would reinforce some of the main ideas and some of the problem-solving strategies. It says a negative charge of negative 55.0 microcoulombs exerts an upward force of 0.200 newtons on an unknown charge 0.3 meters directly below it. So we have a charge, and then directly below it we have an unknown charge. So this charge, I'm going to say, is negative 5.550 microcoulombs. And then directly below it, we have some mystery charge. We know this distance from here to here is 0.3 meters. I'm not going to write all the zeros, but they've given me three significant figures throughout the problem. The first part of the question says, what is the magnitude and sign of the unknown charge? Well, if the force is 0.200 newtons upward, then Q has to be positive because this is a negative charge, and a negative charge would repulse another negative charge, but it will pull upward on a positive charge. So the first thing we know is that Q is positive. To actually get the magnitude, we need to use Coulomb's law. F equals K, Q1, Q2 over the distance squared. I'm going to assume that this is Q1, so this one's Q2. If I solve for Q2, now this is absolute value, which means I don't care about the fact that this is negative. This is only to get the size of the charge. So Q2 would have to equal F R squared over K Q1. And now it's just a matter of filling in the numbers. The force was 0.2, R was 0.3, K was 8.99 times 10 to the 9th. One of the things I did today is I went ahead and stored that in my calculator so I wouldn't have to write it every single time I used it. And the first charge, size only, 0.550 times 10 to the negative 6. Micro is 10 to the negative 6. So once I put all of that in there and punched the buttons, I came up with Q2 is 3.64 times 10 to the negative 6 coulombs. Or if we want to do that with the prefix, remember we said it was positive, we could say that our answer is a positive 3.64 microcoulombs. I don't care if you write the answer in scientific notation with 10 to the negative 6. I don't care if you write it this way. Either one of these is perfectly correct. There is a part B. Part B says, what is the magnitude and direction of the force the unknown charge exerts on the negative 0.550 microcoulomb charge? Well, that one, y'all, is really the easy question. We know, here's our two charges, that they are having an interaction, and that Q2 feels a force that is 0.200 newtons up. That means this particle has to feel an equal opposite force that is 0.200 newtons down. That's the answer to the question. It is a direct result of Newton's third law. If we have an interaction between two charges, both of those charges feel an equal force. In this case, it's an attractive force because we have a positive charge and a negative charge. But the size of the charge, the force that they feel, is the same on both particles. That's always going to be true. And it doesn't matter whether one charge is larger or one charge is smaller. We can see this force formula is going to tell us how large that force is. All right, let's go problem 2. What must the charge, and we want both the sign and the magnitude, so is it positive or negative, and how big is it, of a 1.45 gram particle B for it to remain balanced against gravity when placed in a downward directed electric field of magnitude 650 newtons per coulomb. So we have a particle. It's in an electric field. The electric field points down, it says, and it's equal to 650 newtons per coulomb. In order for the particle to be balanced against gravity, basically they mean it's just hanging in air, the net force has to be 0. That means the downward pull of gravity, which we can get with the formula mg, that's the particle's weight, has to be balanced by an upward electric force. That's going to be QE. All right, if the electric field points down, the force on a positive charge would be down. But the electric force here clearly has to be up. So the first thing that I know is that the particle has to have a negative charge. A negative charge will feel an upward force. All right? These two charges, if the net force has to be 0, it's going to be balanced, then I just know that mg, that's the object's weight, has to equal QE. That's the electrical force. I know the mass, I know the gravitational acceleration G, I know the electric field. I just have to solve for Q. So Q is going to be mg over E. Again, I just have to fill in all the numbers that I know. 1.45 grams is 0.00145 kilograms times 9.80, that's our acceleration due to gravity, divided by the electric field is 650 newtons per coulomb. Notice this, the numerator will come out mg, that's in newtons, and we're going to divide by newtons. This comes out with the correct units, and we get that Q is equal to negative 2.19 times 10 to the negative 5 coulombs. Perfectly good answer right there. I rounded it to 3 significant digits. One could kind of argue right here, maybe it should have been 2. The book used 3, but I kind of think maybe 2 is fine. The other thing we could do is we could write it in terms of microcoulombs. If I want to make this micro is 10 to the negative 6. If I make this 10 to the negative 6, then I have to make this 10 times bigger. So that'd be negative 21.9. If I think I only have 2 significant digits, I might say this is negative 22 microcoulombs. Like I say, I would be flexible on significant digits here. We clearly see 3 here. Honestly, that only looks like 2. Now, maybe the book had an extra one and I didn't write it down. All right, let's look at part B. Part B says, what is the magnitude of an electric field in which the electric force it exerts on a proton is equal in magnitude to the proton's weight? So, same situation, only now instead of having that 1.45 gram particle, a little proton here. It's going to feel a downward force because of gravity. Even protons are affected by gravity. So to balance that out, I'll need an electric force. In fact, I'll need the electric field to point up this time. It doesn't ask about the direction, but if I'm doing part B here, it needs to point up. Again, mg has to equal QE. So if I'm solving for E is going to be mg over Q. So just fill in all these numbers. The mass of that proton is 1.67 times 10 to the negative 27 kilograms. Doesn't weigh very much. The acceleration due to gravity is still 9.80. And I know the charge on my proton is that elementary charge, 1.60 times 10 to the negative 19. Let's see, I typed this in, 1.67 times 10 to the negative 27 times 9.8 divided by the charge, 1.60 times 10 to the negative 19. And I get that the electric field that we're going to need is going to be 1.03 times 10 to the negative 7 newtons per coulomb. It doesn't take a very strong electric field to balance a proton. Well, the weight of a proton is really small. You can look at it. It weighs on the order of 10 to the negative 28. So, I'm sorry, 10 to the negative 26. So it doesn't take a very strong electric field to balance it. Those problems actually use Newton's first law or second law, depending on how you want to think about it. The net force had to be 0 because it was balanced. All right. This one, let's see a little stray mark I made earlier. It says, a charge of negative 3 nanocoulombs is placed on the x-axis at x equal 3 centimeters of an xy coordinate system, and a charge of 2 nanocoulombs is placed on the y-axis at y equal 4 centimeters. If a third charge of 5 nanocoulombs is now placed at the point 3, 4, find the x and y components of the total force exerted on this charge by the other 2 charges. And then we're going to find the magnitude and direction of that total force. A problem like this, the very first thing you need to do is draw a picture. I'm going to kind of do a little labeling too. I'm going to call this Q1. And I'm going to call this one Q2. And then finally this one over here is Q3. I just kind of want to, so if I draw a picture, Q1 is on the x-axis at 3 centimeters. So here's Q1. This is 3 centimeters. Q2 is on the y-axis at 4 centimeters. So here's Q2. And our third charge, which I called Q3, is at the 0.34. So here's Q3. All right, we do need to know the magnitudes of these charges as well. But the first thing I wanted you to really notice, let's see, Q1 is negative. It's negative 3 nanocoulombs. Q2 is positive. It's positive 2 nanocoulombs. And Q3 is also positive. It's 5 nanocoulombs. Those signs help us understand what's going to happen. If we just come over here and we look at Q3, because that's the one we're interested in, we want to find the X and Y components of the total force exerted on Q3 by the other two charges. Since Q1 is negative and Q3 is positive, oops, I got something right where I need to write, so I'm going to erase that. Here's Q3. It's going to feel a downward force because of Q1. I'm going to call that force 1 on 3. Q3 is going to feel a downward force towards Q1. Opposites attract. If we look at the relationship between Q3 and Q2, notice they lie right on this line. That's repulsive. If this is a positive charge, this is a positive charge, it's going to feel a repulsive force directly to the right because of Q2. So I'm going to say this is the force of 2 on 3. So you can see we have two different forces acting on Q3. The really nice thing is this one is completely in the X direction, and this one's completely in the Y direction. It's straight down. So let's go ahead and find the X and Y components. We'll start with the X component. The force in the X direction is going to just be this force 2, 3. What's going on between these two charges? That is, of course, K, Q2, which is 2 nanocoulombs. And, whoops, my pen's been a little ornery. Charge 3 is 5 nanocoulombs. And of course, the distance between them is, we have to look along the x-axis, it's 3 centimeters. 3 centimeters is 0.03 meters squared. So be careful if we have to change centimeters to meters. Like I said, I've already stored K, so I'm not going to write the 8.99 times 10 to the 9th, but that's important. And when I put all of this into my calculator, this came out to be 9.99 times 10 to the negative 5 newtons. Notice it's going to be to the right. Another way of thinking about the right is it's going to be at an angle of 0 degrees. Any way you want to think about it. That force lies in the positive X direction. I'm not sure why I have a cursor blinking there. If I want to get the force of charge 1 on 3, that's going to be K. Q1 was the 3 nanocoulombs. Q3 was the 3 nano. I said that wrong. No, Q3 is 5 nanocoulombs. They have a distance between Q3 and Q1. That's 4 centimeters, so 0.04. Again, I typed that into my calculator, and I see that that force is negative, well, I don't need the negative, it's 8.43 times 10 to the negative 5. This almost got erased there, didn't it? Newtons. And it points down. Or you can think of that as an angle of 270 degrees. I have my x and y components. I can clean them up if I want to a little bit. The x component is 9.99 times 10 to the negative 5th newtons. It points in the positive x direction. We want to clarify that. The y component is negative 8.43 times 10 to the negative 5th newtons because it points in the negative y direction. It points along the negative y-axis. And that makes perfect sense with what I drew up here. The x component pointed to the right, the y component pointed straight down. If we want to add these are perpendicular vectors, x and y components. It's simply a matter of saying, look, I have the x vector points to the right. If I want to graphically add it, it's a little bit bigger than the y vector, 9.99. This is 8.43. The y component points straight down. The sum of those two would start here and end there. That's that resulting vector. I'll put R for resultant. So you can see that as far as getting magnitude, we've done this a lot of times, it's just a Pythagorean theorem. 9.99 times 10 to the negative 5 squared. That's the x component. Negative 8.43 times 10 to the negative 5 squared. That's the y component. You take the square root, and that resulting force has a magnitude of 1.31 times 10 to the negative 4 newtons. Now, it didn't just say get the magnitude. It said find the magnitude and direction of this force. A little common sense says, let me just pick a different color for a second. It should point somewhere down here. I don't know exactly, but something like this. So to get that, we use the tangent inverse. Way back, semester 1, practically the very first week of school, probably we said, to get the angle, we use the fact that theta equals the tangent inverse of the y component over the x component. Now, if the x component is negative, it means we're in quadrant 2 or 3 and we'll have to add 180 degrees. But ours is not. Our x component is positive, so we don't have to add the 180. So it's the tangent inverse y over x negative 8.43 times 10 to the negative 5 positive 9.99 times 10 to the negative 5. Trying to find where I set the page down that has it on there. Let's see. I think it's 40 degrees, but let's double check this. Tangent inverse negative 8.43 divided by 9.99. And the answer comes out to be negative 40 degrees. That's a great answer. I can write it as negative 40 degrees. That means 40 degrees below the positive x-axis. If you don't like writing negative 40 degrees, you could also say it's at positive 320 degrees. That would be the same thing. You'd go all the way around the circle. So here's the positive x-axis. If you're going this way, you have to go all the way around that circle, 320 degrees. Or you can go this way, negative 40 degrees. All right, that's the first 3 problems. I want to stop here. I don't think anybody would want to watch all the solutions in one sitting. But I will make a video that has the remaining problems on it.